Today, I'll be giving a brief presentation on AdaScaleSGD, which is a paper written by the authors seen here that was published in the ICML conference in 2020. The main idea behind this paper is that the authors propose a new dynamic approach for setting the learning rate during large batch training, whereas previous methods used fixed scaling rules that don't adapt to training. AdaScaleSGD uses the gradient's variance to adapt the learning rate properly during training so that we can use any batch size and scale to very large batch sizes while preserving the quality of the model. Our objective can be seen in this expression on the right, where we're trying to minimize some function value big F of W. This function basically equals our expectation for a mini batch taken from our data set of this function little f, which represents our loss for a single mini batch within our data set. So we're trying to minimize the expected loss over a mini batch within our data set. We make a few assumptions about these methods. We assume that big F and little f are differentiable, but we also assume that our mini batch gradient is unbiased. And what does this mean? Well, it just means that if we sample a mini batch from our data set, the expected gradient of the loss over this mini batch will be equal to the gradient of our true objective, this big F of W. Typically, this objective is optimized through stochastic gradient descent. It's kind of the canonical algorithm for solving such a problem. And in SGD, we basically take the gradient of our loss over a single mini batch within our data set, and then we subtract it from the weights of our neural network scaled by some learning rate, seen by these two steps right here. This learning rate can be sampled from a schedule. This could be like a step schedule, a smooth decay schedule, or something like this. And a point of notation, this is kind of how they denote this learning rate schedule within the AdaScaleSGD paper. Basically, we say that our learning rate at a single iteration is equal to this function LR of t, where you sample the learning rate at time step t. And you can use different or arbitrary learning rate schedules for AdaScaleSGD. But more specifically, AdaScaleSGD studies something that's a bit different than stochastic gradient descent. Namely, they study scaled SGD, which basically is SGD, but it applies S mini batches in parallel. So instead of applying one single mini batch, we apply S of them at a time, which basically simulates a large batch size. The issue with this is that we must adapt our learning rate to handle larger batches. So training models in deep learning is obviously expensive, so if we can speed this up in any way, we can train bigger models, expand our capabilities, and so forth. So typically, if we want to speed training up, we need to use some form of distributed training with multiple machines or multiple GPUs, something like this. And there are two ways to distribute training. The first is data parallel training, and the second is model parallel training. Data parallel training is pretty easy to implement. You can see some examples of packages they provide in PyTorch, but it works best if you actually have large batches. So data parallel training operates by maintaining a single global copy of your model across all of the different machines or GPUs, and then splitting your mini batch into multiple pieces so that you can send separate data to each of the workers. So when you do this, communication becomes an issue because when you send different data to each of the workers, you have to synchronize the updates for the global model. You have to make sure that all of these updates that you achieve on the different machines result in the same consistent global model. So in order to amortize this communication cost, we must send more data to each GPU to ensure that it's utilized as much as possible. Large batches also have a couple of nice properties. The first of all being that the variance of the gradient for a large batch is lower. This is because when we take the gradient over our mini batch, there are more examples in it, so the variance of this gradient is obviously lower. And then we can actually achieve convergence in fewer iterations if we have lower variance. We just have to scale up our learning rate. So our overall goal is to get better wall-to-clock time to convergence with equal or better performance than before. And this is done by leveraging the amortized communication costs and data parallel training with large batches, as well as the property of the low variance for the large batches. AdaScaleSGD had several previous state-of-the-art approaches that were used before. One of them would be extensive hyperparameter tuning to try and find the learning rate that works at larger batch sizes, but we're not going to focus on this because it's expensive and requires a lot of compute power. The other accepted rule or widely used rule was the linear scaling rule, which was proposed in the paper seen here. And basically what the linear scaling rule does is it assumes that you have an initial or smaller batch size n and a learning rate nu. And if you scale up to a larger batch size, say you scale your batch size by a factor of m, then you would scale your learning rate by the same factor m. So as you scale up your batch size, you just scale your learning rate by the same factor. The initial results from this method were very promising, and it clearly worked in some cases. And it also had a very simple implementation because you just scale your learning rate as you scale your batch size. However, as was shown in the AdaScaleSGD paper, this actually succeeds in very limited cases, and at greater scale or at greater batch sizes, it can lead to poor performance or even divergence of your model. And it's also a fixed scaling rule, which means it doesn't adapt to the dynamics of training or the things that are going on during training, such as the variance that you're seeing for your gradients. We need some background information about how we define the variance of our gradient, because this will kind of serve as the core of the AdaScaleSGD algorithm. So the expression for the variance of the gradient that's given in the paper can be seen here. And it starts out by taking a covariance from a mini batch drawn from our data set, and this covariance is taken over the gradient of our loss at that mini batch. So because this gradient of our loss is a vector, this covariance will give us a matrix, a covariance matrix, which is transferred here. And we basically, to get the variance, which is defined here, we sum the trace of this covariance matrix. So in result, this is basically computing the variance at each vector position in our gradient, and then taking a sum across all the vector positions, thus summing the variance of the gradient at each vector position. And then this variance is obviously computed across many different mini-batch samples. And remember that data parallelism will actually reduce the variance of this gradient, or if we use larger mini-batches, we'll reduce the variance of this gradient. To motivate the AdaScaleSGD algorithm, the authors present a couple of possible scaling rules that take this form. So you start out with S, which is the number of mini batches that you want to perform in parallel, which determines your large batch size, an initial learning rate, and an initial number of iterations, T1. And then from this, you want to derive the learning rate that you'll use with your large batches, as well as the number of iterations you would have to perform till convergence with your large batches. So the first of these rules is the identity learning rate scaling rule. And this rule actually just does nothing. It leaves both of the hyperparameters the same. And the authors argue that this rule is actually optimal when the mini batch gradients have zero variance. So if the variance of our mini batch is already small, then we actually don't get much benefit from scaling up our mini batch size. So as we talked about in the last slide, one of the benefits of using large batches is that you actually reduce the variance of your gradient over this batch when you have more examples. But this doesn't happen if our variance is already small or zero. So this rule doesn't really reduce the number of iterations that we have to perform, but it's actually optimal in the case of zero variance for our gradient because we don't get much benefit from scaling up our mini batch size. The other rule that's proposed by the authors is the linear scaling rule. And this is actually the previous state of the art upon which AdaScaleSGD is trying to improve. And basically, as we mentioned before, what this does is if you scale up your mini batch size by a factor of S, you scale up your learning rate by the same factor. So what this is doing is it's basically treating stochastic gradient descent as if it's a perfectly parallelizable algorithm. Basically, if we perform S mini batches at the same time inside of one large mini batch, this rule would treat it as if we just perform those in sequence. So this rule actually, as argued by the authors, becomes more optimal as our gradient variance approaches infinity. So if we have a really high gradient variance, this rule becomes more optimal. And this is basically because we get the benefit as we scale up our mini batch size of reducing the variance of our mini batch. So by doing that, we can then increase our learning rate because we will have lower variance within our gradient, which will then allow us to take larger steps towards the optimal position and then converge in fewer iterations. So at this point, the authors had proposed two possible scaling rules. the linear scaling rule and the identity scaling rule. And these are optimal when the variance of our gradient is either infinity or zero. But the issue with this is that in practice, the variance of our gradient is not going to be either zero or infinity. It's going to be somewhere in between these two extremes. So we need a way to find out which one of these rules we actually need to use, or even possibly interpolate between them based on the variance of our gradient. And this is the main idea behind AdaScaleSGD, finding a way to interpolate between these two optimal rules based on the variance of our gradient dynamically during training. So now we make it to the crux of the AdaScaleSGD algorithm, where we want to dynamically interpolate between these two rules, the linear scaling rule and identity scaling rule, that have been proposed by the authors as motivation for the AdaScaleSGD algorithm. So for every iteration for this algorithm, we use a batch size, some base batch size that's multiplied by a factor of s. So our large batch size ends up being s multiplied whatever the small batch size is during every iteration. And then our learning rate is not always multiplied by s, though it's multiplied rather by something we call the gain ratio that's calculated at each iteration. And this is dynamically calculated based on the variance and the gradient of our mini batch. So the idea behind this basically is that our gain ratio represents the number of single batch iterations that are happening within each update. So we also want to keep track of something called scale invariant iterations, which basically just equals the sum of the previous gain ratios. So we can see an outline of the algorithm here in pseudocode, where basically right here, we see that we're tracking the number of total scale invariant iterations that have occurred and make sure that it's less than the total number of scale invariant iterations that we want to perform. And then we start by computing the gradient, which is the average gradient over our large mini batch. So the size of this mini batch will be s times whatever our base batch size is. And then once we've computed this gradient, we compute our gain ratio, which is given by this theoretical expression right here that we'll later have to approximate. And it's based on the variance of the gradient of our mini batch. And the interesting thing about this term that they propose for the gain ratio is that if you look at it, this actually naturally mimics a warm-up schedule during training. So basically, if you look at this term right here, mu, it is equal to the true gradient of our objective. And as we move towards a minimum, this term will move towards zero. Our gradient will approach zero for our true objective as we reach a stationary point. And at this point, this term will actually be equal to s. So we move from the starting point of training when this mu term is large, to having a lower learning rate, to having this gain ratio actually approach s as we approach some optimal point. So we're mimicking a warm-up schedule naturally during training. And then as we see here, once we calculate this gain ratio, we multiply our learning rate by it. So we're scaling our learning rate based on the gain ratio or based on the variance that we're seeing during our gradient during training. And then we apply our update for our average gradient using this new scaled learning rate with the gain ratio. And then again, we keep track of the scale invariant iterations that we're performing so that we know when to stop training. In order to understand AdaScaleSGD, it's important to understand the gain ratio because it's what allows us to interpolate between identity and linear scaling, and in turn what allows the algorithm to work. So when it's proposed in the paper, the gain ratio is given this expression right here, which is a theoretical expression. And this expression is really nice because it allows us to control the number of scale invariant iterations that have occurred. It scales a learning rate based on this gain ratio, naturally mimics a warm-up as mentioned previously, and basically has the property that if the variance of our gradient is very high, this will approach s, and as our variance is low, this term right here will approach 1. So basically this allows us to dampen linear scaling when the gradient variance is not too high. And this is optimal, as we mentioned when introducing the rules previously. The only problem with this is this mu term right here, which is equal to the 2 norm of the squared gradient of our true objective. And we actually don't have access to this gradient of our true objective during training. We only have access to the gradients of our mini batches. So we can't actually compute this during training. We can't do this in practice. So instead, we have to approximate it, and the authors of the paper propose that we approximate it in this way given here. And basically, what this expression is doing is it has this numerator term where you basically take a sum. Remember that for every iteration, we are performing an update using S mini batches. So basically one large batch, but decomposed into S smaller mini batches. So this top term right here is summing over the squared gradient of each mini batch and taking the average of all these squared gradients. And then we take an expectation over that. And then it's basically dividing by the average gradient over the entire large mini batch, the 2 norm of the entire average gradient. And then you also take an expectation. So this expression is nice because it will allow us to actually compute the gain ratio in practice. The only issue is that we really only have access to these gradients for a single large mini batch. We're not tracking them going back in time, but we need to take an expectation over this value throughout training. So the way that the authors propose to do this is using an exponentially decaying average of these squared gradients through training. So basically, you can see similar things with how momentum works and other related things in machine learning. Exponentially weighted average are very common. So basically, the authors just propose that we use this to track this term and update our gain ratio throughout training. And they also, in the ablation, show that AdaScaleSGD is actually robust to the decay ratio that you set for this exponentially decaying average. They claim that they keep momentum constant at 0.9, which is a pretty common default value for momentum throughout training. And they claim that adapting this momentum could be used as some kind of future work. Basically, what they claim is that because this is a less critical hyperparameter and you typically see good performance by setting it at its default value, they just don't tune it and they leave it up to other people or future work to see if you can get better performance by actually tuning the momentum. Additionally, it's good to keep in mind that for AdaScaleSGD, it's not assuming any particular learning rate. So different learning rate schedules can be used or plugged into this algorithm. And then AdaScaleSGD will just scale them accordingly. And it actually, as we mentioned, gives you for free a natural warm-up schedule that occurs during training due to the property of the gain ratio that we discussed. And then no matter what your learning rate schedule is, the scaling will be applied to it accordingly. So now that we've learned the details about AdaScaleSGD, it's good to look at the performance and see if it actually performs well compared to its baselines. So as we can see in the key up here, the authors present 3 different types of experiments, the first of which is AdaScaleSGD, their proposed method, and then they present LSW, which is just the linear scaling rule that we've discussed with a learning rate warm-up schedule, and then LSW+, which is basically the linear learning rate scaling rule with a warm-up, but it instead adopts a number of iterations performed in AdaScaleSGD. And it should be noted that this is not actually feasible. It just uses an informative experiment because they would actually have to run AdaScaleSGD first to get the number of needed iterations, which is not feasible in practice. But when we look at some of the results, the performance of AdaScaleSGD is pretty impressive. So as you can see along this entire row of performance right here, there are really very few divergence cases for AdaScaleSGD, actually no divergence cases, and there are very few cases where the algorithm even performs significantly worse when you scale up the batch size. And this is true for very large batch sizes. Like here with the transformer experiment, we get up to a batch size of 262,000, which is pretty significant. When you compare this to the linear scaling rule, you see that you quickly get deteriorated performance as you scale up the batch size, even in CIFAR 10. When you scale up the batch size to 2,000 elements, you start to see a significant decrease in performance. And in areas like here, you see that the model even begins to diverge, which is not good. So it's clear that AdaScaleSGD has improvements over the linear scaling rule and works in furthermore cases, as well as just larger batch sizes in general. Interestingly, as S increases, or our batch size increases, AdaScaleSGD preserves the model quality really well in comparison to the linear scaling rule, which is what we wanted when performing this in the first place. And additionally, it performs well in a variety of domains. So as you see here, they test this across CFAR10, which is an image data set, ImageNet, which is a larger data set, speech, transformers, and even a YOLO object detector. So in all of these cases, we don't really see any divergence when we scale AdaScaleSGD up to very large batches, which is very good. Another interesting point is that AdaScaleSGD is robust to sudden changes in the batch size. So right here, this elastic with the up arrow or down arrow basically means that during training, they randomly change the batch size and make it larger if there's an up arrow or smaller if there's a down arrow. And even when they implement this change where they scale up the batch size or scale down the batch size significantly at some point during training, the algorithm still performs pretty well, which is pretty interesting because as you see with the linear scaling rule, it begins to perform worse and may even diverge in the case of LSW+. And furthermore, there are basically no failure cases. And this is to be taken with a grain of salt because this is presented by the authors and there are no failure cases in their presented experiments, but from the results presented here, it seems very promising, which makes AdaScaleSGD a very promising algorithm for dealing with large batch sizes. So I want to end this presentation by giving credit to some of the work that I referenced during it. Thank you for listening, and I hope this was helpful. As I said before, this was a presentation on AdaScaleSGD, which was published by the authors seen here. As we've seen, this is a really effective method and hopefully a promising method for scaling generalized models to training with large batches. And hopefully this could be a tool that we could use to move forward in the future and try and create better work with large batch training.